for that, the second idea, so let us call this step 2. The idea is, well, we did AND before, now we are going to do OR, right. So, what do I mean by that? Well, we had g of x as h1 of x, h2 of x and h1 of x, h2 of x dot 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 hk of x. This is what we are at right now, but now what I am going to do is I am going to call this g1 of x and then call these as g1 to k, and then I am not going to just stop with one such g, I am going to use multiple such g's, right. So, now I am going to have g2 of x, which is h21 of x, h22 of x dot 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 h2k of x, and let us say we have gl of x, which is hl1 of x, l2 of x, lk of x. Now, I have L such hash functions in the locality sensitive hashing literature. So, this is called as table 1, this is called as table 2 and this is called as table L, right. So, these are called as tables in I mean, that is more like a computer science data structure kind of a hashing terminology, but you can just think of these as k different functions. Now, the way we are going to define collision is as follows. If I take 2 points, right, so x and y, right, so x and y collide if at least one table matches, right. So, basically for x and y I compute g1 of x, g2 of x till gl of x, g1 of y, g2 of y till gl of y. So, each of these is a k dimensional object and then I match them, and even if I find one match, at least one of these tables match, then I would say that they are colliding, right. So, I care only about points. I am going to measure my distances with respect to only points for which at least one of these hashes collide. Yeah, so that's my, so basically you can think of it as a union kind of a thing, right. So, OR is union, AND is intersection. Here AND means intersection of h1 till h1k should match. Union means at least one of g1 to gl should match, right. So, that's the analog. So, this is going to be my my definition of hash now, right. So, this is the definition of collision. Okay. So, now we have to again fix how many such hash tables that we should combine or take the union of or take the OR of. So, that is a parameter, we will worry about that now. So, for what is the, so what was the goal, right. So, we by doing an AND, the false positive rate went down to the desired levels, but the true positive rate also went down. Now, the hope is that if I do this OR operation, then the true positive rate will go up, right. So, let us see if it does, right. So, let us try to compute the true positive rate of this, of the two step thing that we have been talking about, right. So, what is the chance, right. So, that what is the chance that that two good points or a query point gets hashed to the same bucket as a good point. Of course, the good is relative to the query point that we have. So, how do I calculate this? So, this chance is 1 minus the chance that query does not get hashed to a good point. right. So, well, we want a chance of a query point getting hashed to same bucket as a good point. So, which means it is 1 minus the chance that that event does not happen. So, what does it mean to say that event does not happen? That the event does not happen means that none of the L tables match, right. So, that is what it means, right. So, this is 1 minus none of the L tables match, right. So, that is what it means, right. So, which is, what is the chance that none of the L tables match? Well, what is the chance that one of the L tables does not match, right. So, well, what is the chance that it matches for a good point we know is p1 power k, right. So, which means that 1 minus p1 power k, because we have repeated it k times, right. So, 1 minus p1 power k is the chance that, you know, the first, let us say the first g1 of x matches g1 of q. So g1 of x does not match g1 of q, right. So, p1 power k is the chance that g1 of x matches g1 of q. 1 minus p1 power k is the chance that g1 of x does not match g1 of q. Well, 1 minus p1 of k, p1 power k is also the probability that g2 of x does not match g2 of q, and so on till all the L, right. So, and these are independent. So, the chance that none of the L tables match is this power L, right. So, and 1 minus p1 power k power L is the chance that a query gets hashed to the same bucket as a good point, right. So, how did we arrive at it? Quickly again, we wanted to ask the question, you know, what is the true positive rate, which means that given a query point, you know, we want the probability that you know, g1 of q at least one of g1 of q equals g1 of x, comma g2 of q equals g2 of x dot 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 gk of q equals gk of x happens. At least one of these events happens. That is the true positive rate, because if at least one of them happens, then we declare a collision of between the good point and the q. Well, this is 1 minus p of g1 of q not equals g1 of x and g2 of q not equals g2 of x and dot 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 gk of q not equals gk of x, gl of, this should also be an L, gl of q not equals gl of x, gl of q not equals gl of x, right. So, because even if one matches, then the AND will fail, right. So, because this is the complement property. Now, this is what I am saying is this is because, you know, the fact that g1 of q matches g1 of x or not has nothing to do with g2 of q matches g2 of x, because these are all independent hashes. So, this is just the product of I equals 1 to L probability that gi of q is not equals gi of x, right. So, but what is that? That is product of I equals 1 to L 1 minus the probability that gi of q equals gi of x. And we know that gi of q to match gi of x would mean that, you know, all of the h's in G should match all of the h's in x. So, that is what we have already discussed as 1 minus this value is just p1 power k, and that is why this is 1 minus p1 power k power L, right. So, this is the true positive rate. By a similar argument, we will similarly false positive rate now would be 1 minus p2 power k power L, right. So, that is the same argument, exactly the same argument, but we will get a false positive rate basically, right. So, but let's look at the true positive rate for a minute. and then because that's what we have brought down the false positive. Of course, because of the ORing operation, the false positive will also get affected. We will worry about that a bit later, but first let's worry about the true positive rates to see if we can bring that up, and then we'll worry about how that affects the false positive rate a little later, right? So so what is the true positive rate so far that we have found out is 1 minus P1 power k power L. This is my true positive rate, right? So now what do I want this, right? So so we already have set k to bring the false positive rate in the previous round to certain amount, right? So recall, we already have set k equals, if you go back, so what did we set k to? So this is what we have set k to, log n by log 1 by P2, right? So we have to use that k here, right? So we have already set k to log n by log 1 by P2. So if we set k to that, then what is P1 power k? Let's just do some calculations. This is just calculation. So P1 power k is P1 power log n by log 1 by P2. Yeah. So which is just written differently. I'm going to write this as e power log of P1 power log n by log 1 by P2. That's just to simplify the expression. We'll see how it simplifies, because this is log of P1 power something. So I can write this as e power, I'll bring the power down. So this is log n by log 1 by P2 into log P1. Okay, so which is e power log n into log P1 by log 1 by P2. P1, remember, is a number less than 1, so log P1 is going to be negative. So instead of keeping that as a negative value, let me keep that as a positive value and then make this minus log 1 by P1 by log 1 by P2. So this is multiplying by this, and let's give this a name. So I am going to define rho as log 1 by P1 divided by log 1 by P2, right? So that's just a definition to simplify the notation, and we'll also see it's more than just simplification of notation. This becomes a very important quantity when we do the further analysis. So which means that P1 power k, which is what we are trying to compute, is e power log n into minus rho, which I can write it as e power log n power minus rho, because that's how logs work. And now e and log cancel, so this is just n power minus rho. So P1 power k is just n power minus rho, right? So that's what we have derived, right? So so again, just to quickly go back, we want to look at how much is this true positive rate, and we argued that it is 1 minus P1 power k power L. Of course, we need to find out what is a good L, but then we have already set k. The k that we have set in the previous step is log n by log 1 by P2. Remember, that was set to bring the false positive rate down. Now if I plug in that k, now I want to analyze what is P1 power k, and what I am saying is that P1 power k's value is just n power minus rho, right? So that's what this value is. So now in terms of this rho, the true positive rate can be written as is 1 minus n power minus rho power L, right? So this is what the true positive rate turns out to be. So I should do it like this. Yeah, 1 minus n power minus rho, because this guy is in fact P1 power k. Okay, that's, I can't even see what I've written. So this is P1 power k. for our choice of k. Okay, so now what we are going to do is we need to choose L, right? So that's the whole issue that we are dabbling with, right? So how many times should I do this ORing, right? So we have already decided how many times we should do the ANDing, that's like log n by log 1 by p2, so that the false positive goes down. How many times should we do the OR so that the true positive kind of goes up, right? So now the choice that you can set, right? So you can set L, which is the number of tables that we have, as order of n power rho. That is, L is some theta times n power rho for some constant theta. Theta, think of theta as 1, 2, 3 kind of numbers, and we will see what might be good values in a minute. So if I do that, and the reason why I do that is to simplify my true positive rates, or not just simplify, to get a handle on it. So that will become 1 minus n power 1 minus n power minus rho power some theta times n power rho, right. So now I can think of this as 1 minus n power minus rho power n power rho power theta. But now for large n, right, so this is like 1 minus 1 by x power x. In this case, x is n to the rho, and when n, so, or when x goes to infinity, you know, this is like compound interest kind of a calculation, right. So or you can do some standard calculus limits and then find out, as x becomes larger and larger, 1 minus 1 by x power x tends to, so this guy tends to 1 by e, right. So which means that this whole thing will become 1 minus 1 by e for large n. So of course this is all approximations, close enough, very accurate approximations, by the way, power theta, right. So which means that this is, so the true positive rate is going to be something like 1 minus e power minus theta, right. So well, just to give a sense of numbers, if theta equals 1, the true positive rate, the true positive rate will be, so 1 by e would be something like 0.37, so the true positive rate will be something like 0.63. If I set theta as 2, then true positive rate grows up to 0.86, and if I set theta equals 3, true positive rate will go up to 0.96, right. So remember, what is theta, right. So theta is, you know, so theta is the constant that I am multiplying by n power rho to get the number of tables that I want. Rho itself is log of 1 by p1 by log of 1 by p2, right. So so what I am saying is, you know, I can control the true positive rate to the level I want by setting the number of tables to be some constant times n power rho, where rho is a very critical quantity that depends on, you know, my original hash function, right. So it is p1 p2 sensitive. The moment you give me a p1 p2 sensitive hash function, I can compute log of 1 by p1 by log of 1 by p2, and that gives me rho, and then I will set the number of tables that I need to be n to the rho, right. So some constant times n to the rho, and that constant I can choose based on how much of a true positive rate that I want, right. So what have we done so far? Again, just to summarize, we started with the basic hash function. We ANDed it multiple times. The false positive rate came down to almost a constant, you know, it came down to 1, right. So for I mean, so for the number of bad points that you expect is just 1 if you repeat it k times. But now we are doing an union over L times, right. So and that increases the true positive rate to however close I want to 1 based on, you know, the theta parameter, the number of times I should multiply n power rho, and the number of tables, that the more the number of tables, the better the true positive rate. That's what this is essentially telling me. Now again we have to go back and ask, well, I have tampered with the true positive rate by increasing the number of tables. How does it affect the number of, you know, how does it affect the false positive rate? because then we will, if it does not affect it by too much, then we are happy in some sense, right. So we have kind of controlled both true positive and false positive. So let's ask that question now, right. So so what happens to false positive rate after doing OR? Okay, let's do that analysis. So we know that the false positive rate is the chance that if I have k hashes per table and L tables, then the false positive rate I know is 1 minus P2 power k power L. Like how the true positive was 1 minus P1 power k power L, this is 1 minus P2 power k power L. But then the k was chosen such that P1 power k was n power minus rho there, and then we did that approximation there. So here what happens is, if you remember P2 power k, right. So what was P2 power k? So we chose k, right. So we chose k such that, so P2 power k was actually 1 by n, right. So that's why the false positive rate originally was n into P2 power k, which was like 1, right. So we chose k such that P2 power k was 1 by n, which means that the false positive rate for after repeating it for L tables is something like 1 minus 1 by n power L. Now we have already chosen L, right. So we have chosen L in the previous step, right. So I mean by the previous analysis, L as some theta times n power rho, right. So that's the L that we chose, where just to remind, where rho is log 1 by P1 by log 1 by P2. Okay, so now if I do this, then what will this happen? So first of all, before even applying that, so this for large n, this guy looks like 1 minus 1 by n power L for large n is going to look like 1 minus 1 by n power L looks like e to the minus L by n, right. So this basically looks like e to the minus 1 by e. So the whole thing looks like e to the minus L by n. So now I have chosen L to be theta n power rho. So which means that for our choice of L, this will look like e to the minus n power rho theta n power rho by n, which is 1 minus e to the minus theta n power rho minus 1. So this is how it's going to look like. Now let's look at this a little bit more carefully and see what happens, right. So what we are getting is the false positive rate is approximately 1 minus e to the minus theta n power rho minus 1. So what this will happen is, what will happen now is, for large n, what would happen is n power rho minus 1 would, so let's look at rho for the moment, right. So what will happen to n power rho minus 1? So rho is log of 1 by P1 by log of 1 by P2. P1 is greater than P2, so so 1 by P1 will be less than 1 by P2. So log of 1 by P1 by log of 1 by P2 will be less than 1, right. So because P1 is greater than P2, so which means that this value rho is actually less than 1. Rho is less than 1. So which means that we are basically doing n power something which is negative, because rho minus 1, so rho is less than 1, so this is negative. So which means that for large n, this is like 1 by n power 1 minus rho. So this goes to this will go to 0 because rho is less than 1, because our P1 was greater than P2, right. So, because rho is less than 1, this goes to 0. If this goes to 0, so then what will happen is, you will see that 1 minus, you can approximate for very small values, right. So, this will become smaller and smaller. So, this is 1 minus theta times n rho minus 1, but then this is a very small value, theta is a fixed constant. So, this guy is going to behave like, this is like 1 minus e to the minus theta x, and then that can be approximated for very small values of the power to be something like, you can do Taylor series and show that this is something like, I mean, if I linearize using Taylor series, first order approximation, this will be like n theta n to the rho minus 1, right. So, e to the minus x behaves like x for very, very small values of x, right. So, that is what this means, right. And very, very small values, because for large n, n to the rho minus 1 is going to be very, very small, and so theta times n to the rho minus 1 is going to be very small, and for very small values of theta n power rho minus 1, e to the minus theta n power rho minus 1 behaves something like theta n power rho minus 1, right. So, 1 minus theta n power rho minus 1. So, and so the 1 minus theta n power rho minus 1 will become theta n power rho minus 1, right. So, this will be kind of our false positive rate then, right. So, if this is our false positive rate, so then the number of false positives that we expect to see, right. So, the number of false positives, positive points that is the number of bad guys is going to be n times, approximately going to be n times, because the number of bad guys totally is order of n, the rate itself is theta n to the rho minus 1. So, this is going to be n theta n into theta n power rho minus 1, which is approximately theta times n power rho, right. So, that's what this is going to be.